This is now the 10th lecture of the condensed matter course. When we left off last time, we were talking about lattices in 3 dimensions. And we had covered the simple cubic lattice, or primitive cubic lattice, and we had moved on to the body-centered cubic, cubic lattice, or BCC, or cubic dash I. And we have a picture of that. The conventional unit cell of the body-centered cubic lattice looks something like this. There's 1 point shared among all of the 8 corners, 1/8 times 8 of them, and then 1 in the center of the conventional unit cell, making 2 lattice points in the conventional unit cell. You can look at the thing from above in this plan view scheme where you label all of the heights appropriately. So this point here corresponds to this point here, and it says unlabeled points are at height 0 and A. So this point is at height 0 and height A. Now, if you actually put atoms at the lattice points of the body-centered cubic lattice, you notice that you packed the spheres fairly efficiently. You filled the hole that you would have had if it was just a simple cubic lattice. And because of that, this is a much more common arrangement for atoms. Lots of elements, sodium, lithium, iron, potassium, all take body-centered cubic lattice configurations. It's obvious from this picture that the coordination number, the number of nearest neighbors, is 8. If you think about the sphere in the center, it has obviously 4 neighbors on top and 4 neighbors on bottom, making a total coordination number of 8. It may not be obvious to you that every point in this lattice is equivalent to each other. That's one of our definitions of a lattice, that every lattice point should have the same environment. So we'll look at this picture here. We'll notice this sphere here is obviously in the center of the yellow outline cube, but if we take one of the corners of the yellow outline cube, like that one, it is also in the center of another cube. So each sphere thinks that they're inside a cube. So every point of the lattice is equivalent. That may not be a sufficiently convincing argument to convince you that the BCC is actually a lattice. So what we should do is we should write down the lattice vectors. Lattice vectors, which we'll write as u, v, w times the lattice constant A with the following possibilities. Possibility 1, either, maybe I should say with either. Possibility 1, all, what? The sound is falling out. Can you something's gone wrong? Can someone back there fixing it? Should I use the other microphone, or should I just? I'm
quite happy with it.
No idea. Maybe we kill the sound and then I'll just yell. Is that better? Can someone back there? Yeah. So no, I mean there should be someone back there who's there's not someone back there. I have no idea. Let's keep going and see if we can suffer through it for a while. Someone the person is back there is fixing it. Okay, so hopefully this will get fixed. Stop me if it doesn't. Okay. Anyway, you can still read even if you can't hear. So we're gonna write down the lattice vectors as UVW times A with either all of the UVW integers, and the integer case corresponds to, well, if you look in the conventional unit cell, it's the corners of the unit cell. So this one has coordinate 1, 0, 0. This one has 1, 1, 0, and so forth and so on. The other possibility is UV and W, all half-odd integers, and by half-odd I mean 1/2, 3/2, 5/2, and so forth. And that corresponds to the lattice points in the center of the cube. For example, this point here would have coordinates 1/2, 1/2, 1/2. So this one would be 1/2, 1/2, 1/2. This one would be 1/2, 3/2, 1/2, and so forth and so on. Now, we should check to make one of our definitions of lattice vectors of a lattice are that we should be able to add any 2 lattice vectors together and get another lattice vector. It should be a closed set under addition. So we should check, well, if we add integers to integers, we get back integers, so that's good. If we add integers to half-odd integers, we get back half-odd integers, so that's good. If we add half-odd integers to half-odd integers, we get back integers. So it's going to work either way. Add any of these to each other, you'll get back something that's either this kind or this kind. So that's good. So that makes this a lattice. So let's see. Here we go. There we go. It's useful to write down the primitive lattice vectors, PLVs, for this lattice, which we can take to be 1, 0, 0 times A, 0, 1, 0 times A, and then 1 half, 1 half, 1 half times A. So let's see that on this plot here. So it's 1, 0, 0 times A, 0, 1, 0 times A, and 1 half, 1 half, 1 half times A. And to convince yourself that these things are primitive lattice vectors, all we have to do is convince ourselves that you can get to any point of the lattice by adding these together in integer combinations. So for example, if I wanted to get to this point here, I would take this guy twice, 1, 2, and then subtract this one, and that would take me from here to here, and I'd get to this lattice point. And you can sort of work out that by adding these together in all integer combinations, you can get eventually to every lattice point. Good? So far, so good? All right. Now, a warning, and it's a warning that everyone in the world should take. Do not make the mistake of calling cesium chloride a body-centered cubic lattice. The rule of a lattice is that every lattice point should look identical. So there is a point in the middle of the body here, but it's not identical to the other point, so it's not a body-centered cubic lattice. It's a simple cubic lattice with a basis, and the basis has two inequivalent atoms, one at 0, 0, 0, which is cesium, and the other is at 1 half, 1 half, and 1 half, which is chlorine. Those are different, so it's not body-centered cubic lattice. You will find books that make this mistake. This goes beyond difference in nomenclature. It's just wrong. It is incorrect to call it body-centered cubic lattice. Cesium, pure cesium, where there is a cesium atom at all of the points here, even the one in the center, that is a body-centered cubic lattice. But you're welcome to call it. You're also allowed to call it body-centered cubic is the same thing as simple cubic with a basis, where the basis that we're talking about here includes a point at 0, 0, 0 and a point at 1 half, 1 half, 1 half. Those are equivalent statements. Although I suppose the simpler of these statements is to say it's a body-centered cubic lattice, but you can write a body-centered cubic lattice as just saying a simple cubic with a basis including one lattice point at 0, 0, 0 and one lattice point at 1 half, 1 half, 1 half. Good? So far, so good? All right. Now, you might wonder, why is it we're suffering through using a conventional unit cell that has that has two lattice points in it instead of using a primitive unit cell that only has one lattice point in it? Wouldn't that be easier? Well, there's a reason we don't use a primitive unit cell, because the primitive unit cell is kind of ugly looking. So this is the Wigner-Seitz primitive unit cell for the BCC lattice, and it's a truncated octahedron. I think it has 14 sides. And you can kind of see what's going on here. This is in the center of this cube, there's one of the lattice points, and here are the 8 neighbors, which you can see, all the 8 neighbors. And the hexagonal faces are the perpendicularly bisecting planes between the lattice point in the center of the cube and the lattice point in the corner of the cube. The square faces are the perpendicularly bisecting planes between the lattice point in the center of the cube and the lattice point in the neighbor centering cube. So if you go over one cube and you have a lattice point in the center of that cube and you make the perpendicular bisecting plane, that gives you these square faces. Remember, the way you construct the Wigner-Seitz cell is by making perpendicular bisectors, so you know that everything in space that's closest to the one lattice point in the center is on the inside of that object. So it's an ugly shaped object. That's why we don't use primitive unit cells for the BCC lattice. But if you do take these ugly shaped objects, these truncated octahedrons, they will stack together very nicely and tile all of space, filling all of space appropriately as they're supposed to. Okay? There's one more type of lattice that we need to discuss, which is the face-centered cubic lattice. Face-centered cubic, or FCC, or cubic-F. You may have noticed I wrote centered the American way, not the British way. And the reason I do this is because if I did it the other way, my brain would explode. It's just, you get used to doing something one way and then you just can't change. Either way is correct, so depending on what side of the ocean you're on. So let's see what the face-centered cubic lattice looks like. So you start with the simple cubic lattice, the points in the corner of the conventional unit cell, and then you add 1 point in the center of every face, like this one in the center of this face, this one in the center of this face, this one in the center of this face, and so forth. How many lattice points are there in the... So the... I'm going to have to make these harder. Yes, there are 4 points in the conventional unit cell. There's, to see where the 4 points are, there's 8 corners, each of which counts 1/8. So it's 1/8 inside the conventional unit cell. Then there are 6 faces, and the point in the center of the face is half inside the unit cell and half outside the unit cell. So it's 6 times 1/2 equals 4 lattice points within the conventional unit cell. You can also draw the conventional unit cell with this plan view scheme, which, so here are the points in the corners. As it says, unlabeled points are at height 0 and a. So this point here corresponds to this point here, which is at height 0 and a. You can see the points on the halfway up the faces at height labeled a over 2. So that's this point, this point, this point, and this point. That's this one, this one, this one, and this one. And then the one in the center here is also at height 0 and a, this one, and this one here. Okay? Now, if you imagine arranging atoms together or spheres together in the FCC lattice configuration, it is actually the most efficient way that you can possibly pack spheres together. So if you have a bunch of tennis balls, you're trying to stick them into a box, the highest density packing of those tennis balls into the box is an FCC lattice. There are other packings which are equivalently dense, but you're never going to do better than the FCC packing. We don't study the other types of packings because they don't have orthogonal axes, but they're equivalent to FCC. In fact, the statement that you can't get a more dense packing of atoms than FCC was conjectured by Kepler in 1611, and it was only proven in 1998. So it's a very long-standing theorem, but it turns out to be true. You can't do any better. You can't pack more things into a small space, if they're spheres, than using FCC lattice. Because you get so many spheres in a small space, if you think about atoms trying to attract each other, it's a very appealing configuration for atoms, and so many elements take FCC configurations. Copper, silver, gold, calcium, many others are FCC. Okay, so since there are 4 atoms per unit cell, we should be able to view the FCC lattice as 4 interpenetrating simple cubic lattices. So let's see if we can see that. This is an FCC lattice of spheres, and this is the red I have marked out a simple cubic lattice. This is a simple cube. It's a little hard to see. But then you can actually pick out, if you look very carefully, there are 3 other interpenetrating simple cubic lattices which are mixed in here. And although it may not be completely obvious, that the environment of every single sphere is identical to the environment of every other sphere. Now, since that's not completely obvious, we should do the exercise of actually writing down the lattice vectors. Lattice vectors for the FCC lattice. And I claim they take the form, again, UVW times A, where either 1, UVW all integer, and again, that would correspond, backing up one more, that would correspond to the points in the corners, all integers. So this one is 1, 0, 0, this is 1, 1, 0, and so forth and so on. The other possibility, so UVW, where either possibility 1, they're all integers, or 2, 2 of them are half odd integer, and 1 integer. Okay, so we're going to show that this actually works, but before going on, so for the one more chocolate, what is the coordination of... The coordination number is 12. Let's actually see on this plot why it is the coordination number is 12. I'm going to stop asking questions. I'm going to run out of chocolate this way. I'm going to have to ask harder questions. Okay, so to see the coordination numbers 12, let's take this sphere here, the one that's cut in half. It has 4 neighbors, 1, 2, 3, 4, at the same height. It has 4 neighbors at a slightly lower height. Here you can see 2 of them that are touching it also. And then if you went to a slightly higher height, the same distance up that these are down, you would have 4 more. So there's 4 at the same height, 4 slightly lower, and 4 slightly higher, which may not look all that convincing, but we can show it using this rule. So this rule would give that to us for free. The reason we would know this is because if you look at this point here, well, first of all, let's take a look at this item 2 here. 2 of them half odd integer, 1 of them integer. What does that correspond to? That corresponds to someone in the middle of the face. For example, this guy here, he's over 1/2, he's back 1/2, but he's up an integer height. Whereas this guy over here, he's over 1/2, he's up 1/2, but his height is an integer, happens to be, his depth is an integer. This one here is over 1/2, up 1/2, and he's an integer back. So if it's on a face, it has 2 half-odd integers and 1 integer. If it's on a corner, it's all integers. Now, we can check here that, again, we should have the rule that if you add any 2 things from these sets to each other, you should get back something from one of these sets. So, for example, if you add integers to integers, you get back integers. If you add integers to half-odd integers and 1 integer, you'll get back, the fact that you're adding integers to something doesn't change whether it's a half-odd integer or an integer, so you get back something in set 2 again. But what's not obvious is you take 2 things which have 2 half-odd integers and 1 integer, and you add them together, what do you get? So let's try. So if you have, for example, 1/2, 1/2, 1, and you add it to 3/2, 1/2, 0, so both of these are 2 of them half-odd integers, 1 of them integers, so both of these would be on the face. You get 2, 1, 1, which is all integers, and that's good. But I could have done it differently. You could have had 1/2, 1/2, 1 added to, say, 1/2, 0, 3/2, for example. Then what you get is 1, 1/2, 3/2, and still 2 of them are half-odd integers and 1 of them is an integer. So if you add together 2 things from set B, you'll get either something from set 2, you get either something from set 1 or something from set 2. So it forms a closed set under addition. Now, given that we know that these are the coordinates of the vectors in the FCC lattice, let's see if we can figure out that coordination number 12 a little more easily. So let's start with this point here. That's the point 0, 0, 0, and look for the closest things to 0, 0, 0. Closest to 0, 0, 0. Okay. Well, okay, this guy here looks pretty close. His coordinate is 1/2, 1/2, 0. So 1/2, 1/2, 0. And that fits the definition of one of the points in the FCC lattice, 2 of them half-odd integers, 1 of them integer. And it's pretty close. Can't get any closer. But we could have made this plus or minus, and we could have made this plus or minus as well, right? That those all fit the definition as well. And we could have put the 0 in any of the 3 spots, 3 possibilities. So we have 4 possibilities of these plus or minus signs and 3 possibilities of where we put the 0. So we get 4 times 3 equals 12 is the coordination number. Okay? Good? Okay. All right. So it's worth also writing down a set of primitive lattice vectors for the FCC lattice. So PLVs for the FCC lattice, a really good example are just the closest vectors make pretty good PLVs. So 1/2, 1/2, 0 times A, 1/2, 0, 1/2 times A, and 0, 1/2, 1/2 times A make pretty good primitive lattice vectors. There they are. And again, to convince yourself that they really are primitive lattice vectors, what we have to do is convince ourselves that we can get to every point on the FCC lattice by adding integer combinations of them. So for example, if we wanted to get to this point here, we would have to add 1 of each of them. So this one, plus this one would take us to here. And if we wanted to get to here, we would have to add, well, I'm not sure. Yeah, okay. How do you get there? 2 of these, and then minus 1 of these or something. And anyway, so you can play around with it. It works. You can get there. how do you get here? Yeah, so it would be 2 of these would get you here. Then you need maybe minus 1. Yeah, minus 1 of these, then plus 1 of these, or something like that. That will get you there. Okay. Anyway, all right. So since the FCC lattice has 4 lattice points per conventional unit cell, just like we did with the BCC, we could write it as simple cubic times a basis, where the basis now includes basis equals the point at 0, 0, 0, the point at 1/2, 1/2, 0, the point at 1/2, 0, 1/2, and the point at 0, 1/2, 1/2. That would give me the 4 lattice points per unit cell. And if I translate those 4 lattice points in my conventional unit cell around to every lattice point, so lattice point is at 0, 0, 0, and then these are all displaced from the original lattice point, that will reconstruct the entire face-centered cubic lattice. Or another way of thinking about it is these are the displacements of the 4 interpenetrating simple cubic lattices that make up the FCC lattice. As with the BCC lattice, there's a reason we don't use the primitive unit cell. We use a conventional unit cell, not the primitive unit cell, because the primitive unit cell is extremely ugly. Here it is. It's a truncated dodecahedron. It has 12 sides. Those 12 sides correspond to the 12 nearest neighbors. So what we have in the center is one of the lattice points, and then we have the 12 nearest neighbors, 4 of them slightly above, 4 of them at the same height, and 4 of them slightly below. And the faces of the truncated dodecahedron here are the perpendicular bisectors of the segment between 0 and the nearest neighbors. Okay? All right, that's all we need to know about the FCC lattice. In fact, that's all the 3-dimensional lattices we're going to study. It is worth knowing that there are 14 types of lattices in all. The ones we've studied are the cubic primitive, the cubic body-centered, the cubic face-centered. We also talked about the tetragonal, simple tetragonal, and simple orthorhombic. And then you have a whole bunch of other ones here. You may notice that there's analogs that we don't need to know. Analogs of the body-centered tetragonal, body-centered orthorhombic, face-centered orthorhombic, and so forth. You may notice there's no face-centered tetragonal. The reason for that is because, in fact, by turning the lattice sideways, it would be in one of the other classes as well, so you would be overcounting. So anyway, these are sometimes known as the Bravais lattice types, after Bravais, who is the first person to write them down correctly. And so we give Bravais credit for doing them. So these are the only possible lattice types you can have. It's kind of a deep mathematical statement that any periodic structure in 3 dimensions, anything you can have in 3 dimensions, is one of these lattices times some basis. So if you can write down all these lattices and you can have any basis you choose, no matter how complicated, you can make anything. Any periodic structure is one of these lattices times some basis. The only ones we're actually going to have to know this year are the 3 cubics and the 3 simple cubic tetragonal and orthorhombic. Very rarely do we need to know tetragonal or orthorhombic. I think they only rarely come up on exams. It's really these 3 across the top that actually show up on exams. Okay, so this is an example of what you can put together when you have a lattice and a basis. This is a sodium chloride structure, a very typical salt structure. Sodium chloride, very ionic. Sodium gives up the electron. Chlorine takes the electron. And if you look at it carefully, you can see that sodium is forming an FCC lattice. It's even labeled cubic F. So maybe it's easiest to see in this picture. These are all depictions of the same lattice. None of them are actually great, but we may have to make do. So here you can see the green spheres here in this picture form an FCC lattice. So it's on the corners and in the center of the faces as well. But in addition to the sodium atoms, which are on the FCC lattice, there are chlorine atoms as well. And you can describe the position of the chlorine atoms by saying for every sodium atom, there is a chlorine atom displaced by 1/2, 1/2, 1/2 from the sodium atom. That will get you the position of all the chlorine atoms. Here's a plan view. The blues would be the sodiums and the chlorines. So for example, if I started a sodium and I go over 1/2, back 1/2, and then up 1/2 to the next layer, I get to a chlorine atom. When you describe a basis, you should always describe the basis of the primitive unit cell. So here, I don't tell you where all the four, I don't talk about the conventional unit cell, which would have 4 sodiums and 4 chlorines. I just tell you it's an FCC lattice, and immediately you know that the conventional unit cell will have 4 lattice points in it. And on the position of the lattice at 0, 0, 0, there's a sodium, blue, and then displaced from that by a half, I put a chlorine. So I only have to describe to you 1 sodium and 1 chlorine to tell you everything once I've told you it's a simple cubic, it's a FCC lattice. Notice also that it's not unique how I describe the position of the chlorine with respect to the position of the sodium. I could have told you that the chlorine was displaced 1/2, 0, 0. That would give you the equivalent structure. Or I could have decided that chlorine was my 0, 0, 0, and sodium was displaced from it. That would also give you an equivalent structure. So there's various different ways to describe the same lattice. Here's another structure that we run into very frequently, the diamond structure, carbon. It also is the structure of silicon and germanium. It is also based on the FCC lattice. So you can see, for example, in the top face here, there's some guy, there's one in all the corners, and there's one in the center of the face. The side face, there's one in all the corners, there's one in the center of the face, and so forth. So it definitely has an FCC lattice in it. But then that doesn't tell you where all the positions of the carbons are. There are additional carbons, and you can describe the position of the carbons as being displaced by 1/4, 1/4, 1/4 from every lattice point. So for example, in the plan view, we start with this carbon at 0, 0, 0, and then we displace by 1/4, 1/4, 1/4, and we find another carbon at that position as well. So again, I don't have to describe the position of all of the 8 carbons in the conventional unit cell. I only have to tell you that it's an FCC lattice, and it has a basis of 2 atoms, one at 0, 0, 0, and one at 1/4, 1/4, 1/4, and that's sufficient to describe everything. Okay? All right, what's the lattice? What is the lattice? What is the lattice? What? It is a lattice. It's a lattice with a basis. What lattice type? Who said it? FCC? Okay, good. Wow. See, there's an advantage to sitting up close. You get more chocolate that way. Incidentally, I switched from chocolate types because I tried some of the chocolate yesterday. It wasn't all that good, so hopefully this is better. I'm a chocolate connoisseur. Okay, so it's FCC. So this is gallium arsenide structure, also known as the zinc blende structure. It's exactly the same as the diamond structure, except that you've taken the second carbon and you turn it into a different type of atom. So here, let me actually just show you. So the yellow form an FCC. So you can see that the yellow atoms are in the corners and the center of the faces. So for example, here's a face, and there's a yellow in the center of it. Then the blues are displaced 1/4, 1/4, 1/4 from every yellow atom. Now, some of it may look a little puzzling. It looks like we have more yellow atoms than we have blue atoms, but we don't, because some of the yellow atoms are only half inside the unit cell. The FCC, there's 4 lattice points within the unit cell, and so there should be 4 yellow atoms if you count them, including half, an eighth if it's on the corner and a half if it's on the side. You'll count 4 yellow atoms, and then there are obviously 4 blue atoms completely inside the unit cell as well. Okay. One more comment. This is a subtlety. If Mike Glazer happens to be your tutor, he'll be very happy that I tell you this. He's a real crystallographer, and he always holds my feet to the fire to force me to tell things the way they really are and not tell any lies. So here I'm going to tell you the subtlety and not tell you any lies. So suppose we have a material like this. It appears to be a simple cubic system with a basis of 3. There's 1 on the corners and then 2 somewhere in the center. They're not right in the center, so it's not BCC. But there's 2 somewhere in the center, and there's 1 shared by all the 8 corners. So we would say it's a simple cubic with a basis including 3 atoms. Now, if I measure the edges of this cube and I say they're all the same, A, and A in all the 3 directions, I would say you would be tempted to say it's simple cubic crystal. But a crystallographer would say it's not. And the reason they would say it's not is because it doesn't have the symmetry of a simple cubic object. A simple cubic object, you should be able to turn it in all 6 directions, and it should look the same whichever direction you look at it from. And this thing doesn't look the same if you look at it from the top as if you look at it from the side. Why is that important? Well, the crystallographer knows that if it doesn't have the symmetry, there's no good reason that its height should be the same as its width. They're not the same. They're not equivalent in any sense. So the height doesn't have to be the same as the width. And so if I tell you, well, the edges have the same length, he would say, well, go measure it more carefully, and you'll discover they're not the same length. So the crystallographer knows if there's not a good symmetry reason for the edge lengths to be the same, then they're not the same. And a crystallographer, if I wrote this down, a crystallographer would come back to me and say, no, they're actually not the same length. You just think they're the same length. So go measure it again and you'll discover that they're not the same length. It would be an unbelievable coincidence if there was not a good symmetry reason for the edges to be the same length and they ended up being the same length, okay? So that's to make the real crystallographers happy. And that is all we have to say about crystal structure for today. Okay, good. So we've now learned everything we need to know about crystal structure in 3 dimensions. All the lattices we're going to have to discuss. We know about lattices and bases. But at the end of the day, we really want to describe physical phenomena in these crystals. And more often than not, what we're interested in is waves of some sort, whether they're vibrational waves or phonons, whether they're electron waves, whether they're electromagnetic waves. And the world of waves is the world of reciprocal space. So we have to back up and understand some things about reciprocal space when we have complicated crystals. So let's remind ourselves some things we learned about reciprocal space in 1 dimension. Well, in 1 dimension, we had a direct lattice of the form R sub n equals A times n. N was the integer. A was the primitive lattice vector, PLV. And then from direct space, we have the reciprocal space, reciprocal lattice, which we can write as Gm equals 2 pi over A times m. Now here, 2 pi over A is the primitive lattice vector in reciprocal space, primitive lattice vector for the reciprocal lattice. Now, why was it that we chose this to be the reciprocal lattice? Well, we chose it because if you take k to k plus any element gm in the reciprocal lattice, we get back the same wave. Gets same wave. And why is that? Well, let's do it carefully. E to the I k dot r, k dot r gets shifted to e to the I k plus g m dot rn, and that becomes equals e to the I k dot rn, e to the I gm rn. And this factor here is just 1 because this is 1 because it is e to the I 2 pi over a times m times a times n. And that's just 1. So we're going to generalize that into more dimensions. In any dimension, we define the reciprocal lattice, define recip lattice, recip lat via points as points g vector such that e to the I g m dot rn, okay, g, let's not put an index on it yet, g dot rn equals 1 for all r n in direct lattice. In direct lattice. So this is our general definition of the reciprocal lattice vectors g in the reciprocal lattice. Now, this is a nice definition. It's a very useful definition, but I have not in any way proven to you that this definition defines a lattice. I've claimed it defines a lattice, but I haven't shown you it defines a lattice. And the proof that the set of points g in reciprocal space that satisfy this equation equals 1 for all Rn in the direct lattice, the proof that that defines a lattice in reciprocal space is a little subtle and a little tricky. So we're going to go through it and see if we can make it convincing that it's true. So first of all, we'll take the direct lattice vectors. We have to define the direct lattice vectors. Direct lattice vectors, x. We'll write them in terms of the primitive lattice vectors. So R equals n1, a1, plus n2, a2, plus n3, a3, where the a's are the primitive lattice vectors, a's are PLVs. A's are PLVs. Are the primitive lattice vectors. Okay, so we've defined the direct lattice now. And then we're going to guess. I'm going to make a guess of what, this is a very good guess, It's a correct guess, and we're going to have to prove it in a moment. Guess the PLVs of the reciprocal lattice, of reciplat. We'll call them B sub I as compared to A sub I for the direct lattice. And we'll define them by the following equation. B sub I dotted with A sub j equals 2 pi delta ij. It's a rather important equation. Now, first thing you might wonder is, how do I know, given a set of primitive lattice vectors in direct space A, how do I know that there's a set of vectors B which satisfies this, this equation, sort of a dual space, dual vector space basis? Well, there's a fairly easy way to show you that you can find B's given some A's, which is by writing them down. So let's write them down. So Bi equals 2 pi aj cross ak over, let's see, a1 dotted into a2 cross a3. Okay? And this is for ijk equals to 1, 2, 3, or 3, 1, 2, or 2, 3, 1. So in the cyclical way. So I claim that this expression for B will satisfy this definition of B. And to check it, let's just find out if it's true. So let's take, for example, B1 dotted with A1. So we'll write out B1. B1 is 2 pi A2 cross A3 over A1 dotted with A2 cross A3. And then we want to dot that into A1. And we see that the numerator and the denominator are actually identical. So we just get 2 pi, as we're supposed to. However, if we took B1 dotted into A2, we would get the same expression here, A2 cross A3 up top, and then this whole expression downstairs, which I'm not going to write, and then dotted into A2, and that thing equals 0, because A2 cross A3 is orthogonal to A2. When you dot it into A2, you get 0. So indeed, the B1 in dot A1 gives you 2 pi, B1 dot A2 gives you 0, and you can check that it works for all the other ij combinations as well. Okay, so now we have a guess for what our reciprocal lattice vectors are. So we would guess that we would write down our reciprocal lattice vectors G as M1 B1 plus M2 B2 plus M3 B3. Okay, that's going to be our guess right now. But if we wanted to try to prove that these G's are reciprocal lattice vectors, if we want to prove that G is a lattice, what we need to show is that the M's can only be integers. Okay? Now, if I want to just pick any point in reciprocal space, I can choose to write that point as G with M's arbitrary. So let me start with M's arbitrary. M's arbitrary. In other words, real numbers, arbitrary. And that allows, i.e., consider any G, consider any vector, any vec, G, not necessarily on a lattice. So I'm going to consider any possible G to begin with. Now, then what we're going to do is we're going to impose the definition e to the I G dot R equals 1. So we're going to force on it 1 equals e to the I G dot R. Okay, what does that mean? E to the I, okay, G is M1 B1 plus M2 B2 plus M3 B3. I'm about to run out of room. N1 A1 A1 plus N2 A2 plus N3 A3. Okay, and I need this to, if I'm going to impose the condition e to the I G dot R equals 1, I have to impose the condition that this thing equals 1. Well, using our orthogonality condition Bi dot Aj equals 2 pi delta Ij, that is 1 equals e to the 2 pi I M1 N1 plus M2 N2 plus M3 N3. Now, if I want this thing to equal 1 for every possible direct lattice vector, for every possible n, the only way this will be true, this is true for all n, n, only if m are integers. M's are integers. Okay? So that means that in order to satisfy our definition of the reciprocal lattice that e to the I g dot r equals 1 for all r in the direct lattice, the only way we can do that is if we choose g of that form with the m's integers. Therefore, g is a lattice. And not only do we know that g is a lattice, we know what its primitive lattice vectors are. So we just derived the fact that g is a lattice with those primitive lattice vectors. So far, so good? Happy with that? OK, good. A couple of interesting facts. Actually, I think this is a homework problem. It may be on the revision homework or something. The reciplat of FCC is BCC. BCC and vice versa. Kind of an interesting statement. You can check it, and I think you probably will for one of your homeworks. Another interesting comment is that in 2D, same rules apply. Rules apply. But you might wonder, how do you handle this formula in 2D because I only have 2 vectors, not 3? Well, the way you handle that formula is just choose A3 equals z hat, a point coming out of the plane. So in other words, if you live in 2D, you imagine there's a normal to a plane, and you treat that as your third primitive lattice vector, and you go from there, and you're in business. All right, a couple minutes left. We're going to try to, in the next couple lectures, we're going to try to do some interpretation and some uses of this reciprocal lattice. There's a rather important statement that people frequently make. The reciprocal lattice is the Fourier transform of direct. This maybe isn't surprising because the reciprocal lattice lives in K space and the direct lattice lives in real R space. And we know to get from R space to K space, you frequently have to do things like Fourier transform. But let me see if we can make this a little bit more rigorous. Let's do it in 1D again. So our lattice vectors Rn equals A times n. And how are we going to Fourier transform that lattice? Well, let's make a function, rho of x, which is a sum over all lattice points of a delta function at the position of each lattice point. Okay? This is what's known as a delta function comb. Delta function comb. Have you seen this before in quantum mechanics or something? Comb? Okay. It looks kind of like this. Here's the x-axis, and then here's 0. Here's A, here's 2A, 3A, and it has these great big delta function peaks at the position of each of these lattice points. Okay, now let's try Fourier transforming it. So Fourier transform of rho of x equals integral dx e to the I kx. Then we have this rho of x function, and we'll plug in the rho of x function. We'll pull out the sum, so we get sum over n, integral dx, e to the I kx, and delta function of x minus Rn. And we let the delta function act, so we get sum over n, e to the I k Rn, which we could also write as sum over n, e to the I k a n. Okay? So what is this? We have this Fourier transform of rho of x, and it's a sum over all of these phases, e to the I k Rn. Well, if k is an element of the reciprocal lattice of Gm, then every term here is of the form e to the I gn Rn, Gm Rn, and so every term is 1. So this then becomes sum over n of the number 1, which is infinite, if you have an infinitely big system. If k is not an element of the reciprocal lattice, then what do we have? Then what we have is you'll have a situation where this complex phase here is not equal to 1. So it has some complex phase, some arbitrary complex phase. And then if you go out to a lattice point which is twice as big, double n, you'll get twice the complex phase. And you go out to something that's 3 times as big, you'll get 3 times the complex phase. And these complex phases keep rotating around and around and around. So you get sum over oscillating phases, which goes to 0. They all cancel out, and you get 0. So at the end of the day, maybe I'll move over to here. What we have is that the Fourier transform of this delta function comb is a sum over all possible reciprocal lattice vectors, k minus gm, of a peak, an infinitely big peak, at the position of the reciprocal lattice vector. And if you do it carefully, you get a factor of 2 pi over a out front. A being the lattice vector. This 2 pi over a it's the same 2 pi that shows up whenever you do Fourier transforms. There's always 2 pi's floating around. So they're always there. You're not probably going to be held responsible for ever getting this prefactor right, I suspect. So the principle is that if we have a delta function comb in real space, if you Fourier transform that, the result is infinite if you're sitting on a reciprocal lattice site, if your k is a reciprocal lattice vector, and it's 0 otherwise, and that becomes a delta function comb in k space. Okay? Now, the same thing more or less holds in 3 dimensions. So let's see if we can do this in 3D. So in 3D, we'll write rho of x vector equals sum over lattice points r of a delta function x minus r. Again, if you Fourier transform it, you'll get Fourier transform of rho of x. You let the delta function act, and it's now a 3-dimensional delta function, delta 3. This becomes sum over lattice vectors r of e to the I k dot r. And then this thing becomes exactly in the same way, that if k is a reciprocal lattice vector, it's the sum over an infinite number of lattice vectors of the number 1, which diverges, and you get infinity. If k is not a reciprocal lattice vector, then you don't get the number 1. You get some complex phase, and that complex phase rotates around and around and around, and when you add them up, you get 0. So you end up getting 2 pi cubed over the volume of the unit cell. Volume unit cell. Again, you're probably not going to be held responsible for the prefactor. Sum over reciprocal lattice vectors of k minus reciprocal lattice vector g. Okay? So far, so good. Now, we can do a little better even. We can consider things that are more complicated than just a delta function comb, because we're very infrequently actually presented with a real delta function comb. So instead, we're going to consider any periodic function, rho of x. And what I mean by periodic function is that rho of x should equal rho of x plus r, where r is a lattice vector, lat vec. So this function, rho of x equals rho of x plus r, where r is a lattice vector, it has the periodicity of the lattice. Okay, does that make sense? Yeah? Okay. Okay, so now let's take the Fourier transform of this function. Fourier transform of rho of x equals integral d3x e to the I k dot x, and this is the integral over all space, rho of x. Now, we're going to do a little bit of a trick. This is a useful trick that will probably come back to haunt you at some point. I'm going to take that integral over all space, and I'm going to write it as an integral over all lattice vectors r, then the integral d3x over the unit cell, maybe the Wigner-Seitz unit cell around r. So I'm just breaking up that integral over all space into pieces, each piece being over the Wigner-Seitz cell around the position r, e to the I k dot x rho of x. Then what we'll do is we'll define a parameter y, x equals r plus y, like that. And we'll rewrite that integral then as integral, sum over r, integral d3y of, over the unit cell, of e to the I k dot, I guess, r plus y, and then rho of r plus y. Now, rho of r plus y, rho is periodic, so rho of r plus y is the same as rho of y. So that makes that easy. And then I can factor out the e to the I k dot r term from this here, and I get sum over r, e to the I k dot r, put that in parentheses, times, this in parentheses, integral d3y over the unit cell of e to the I k dot y of rho of y. Now, this first term should look familiar since we just calculated it a moment ago. This thing here is the sum over all lattice vectors of e to the I k dot r. If k is a reciprocal lattice vector, this is infinite. If k is not a reciprocal lattice vector, this thing is 0. So this thing, just as we had before, is 2 pi cubed over the volume of the unit cell, sum over all reciprocal lattice vectors, g, of delta of r of k minus g. So it gives you a delta function peak at the position of each reciprocal lattice vector. This term here is known as the structure factor, S of k, structure factor. Structure factor. And it's just the Fourier transform of the function we're considering within a single unit cell. So this is actually a rather interesting statement, a rather important statement we're going to use many times later on. If you take any periodic function whatsoever, you Fourier transform it, it will only have non-zero values at the position of reciprocal lattice vectors. And its value at those reciprocal lattice vectors is weighted by the Fourier transform of the function within a single unit cell. This is going to be extremely important in the next 2 or 3 lectures. So I will see you on Monday? I think I'll see you Monday. All right. Have a good weekend.